All right. Going into Blackboard. This week's announcement. Oops. You have the rest of chapter 3 is due this week. And your final quiz for this section, this module, is due. So your first exam is going to be next week, due a Wednesday, September the 21st at 11:59. What you are allowed on an exam, what you're allowed to use for your exam is 1 page front and back of notes that you've created. You can use your graphing and or your scientific calculator. You can use one or both. You can have both of those out. You may not use your cell phone. Every exam has a review. The review is always due the day before the exam. So your exam 1 review is due Tuesday, September the 20th. To receive partial credit, you must submit your exam work. Otherwise, I won't even look at your exam. It's probably less likely for you to make typos in statistics than it was for you to make typos in college algebra. That it's a lot easier to make a typo in my math lab than it is in my open math. But that the only way I will check for anything is if you turn in a paper. As a matter of fact, if you turn in a paper, I will check all your problems. It has to be neat and somewhat in order. You have to label the problem numbers. If I get a piece of paper that's written in every single solitary direction all over with nothing numbered, I'm just going to put it aside and not look at it. It's too frustrating and anxiety ridden to do that. I get all anxious trying to find your problems. So I won't do that. All right. So your first exam will be due a week from tomorrow. All right, so let's finish up chapter 3. We had talked about the 2 basic rules of probability. We had looked at contingency tables. So we are ready for Venn diagrams and tree diagrams. And both of these are ways of displaying our sample space. And a tree diagram can be especially helpful when we look at Bayes' theorem, when we look at conditional probabilities, which we will do in our last example in this chapter. Okay, so just a way of us creating our sample space. A tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and to solve. The following example illustrates how to use a tree diagram. In an urn, do you even know what an urn is? A vessel. In an urn, there are 2 balls. One red ball, which we're going to denote as capital R, and one blue ball, which we're going to denote as capital B. Draw 2 balls one at a time with replacement. With replacement means that you put the first ball back in the urn before you select the second ball. The tree diagram using frequencies that create a tree diagram using frequencies that show all the possible outcomes. Or it says as follows. I'm going to draw it. Okay, in the first draw, you have one blue ball and one red ball. So in the first draw, we're going to draw branches that denote what can happen on that first draw. I can either get a blue ball or I can get a red ball. So we have two branches. One that represents I can draw a blue ball out of this urn. The other that represents I can draw a red ball out of this urn. Okay, one of those two things can happen. Put the ball back in the urn and draw a second time. So now this is my second draw. What can happen if I drew a blue ball out the first time? The second draw, I could get a blue ball or I could get a red ball. So we're going to, again, create two branches, one of which is blue, one of which is red. Let's put this B up here. All right, what happens on the second draw if I drew out a red ball on the first draw? Well, again, I could get a blue ball or I could get a red ball. So what are the results, the sample space of this experiment? I could get two blue balls. So following the first branch and the second branch, I could get two balls that are blue. Or I could get what? Blue or red. Put this a little bit closer here. Okay, if I follow the second branch in the first draw, I could get what? Red, blue. Or I could get red, red. So my sample space consists of these four possible outcomes. Both balls could be blue. The first one could be blue, the second one could be red, or the first one could be red, the second one could be blue, or they could both be red. So the tree diagram, I get all the possible outcomes. And this is my sample space. And from there, I can find probabilities. What's the probability of me getting both balls are blue? First draw is a blue and the second ball is a blue. Is that 1 out of 4? So I can create probabilities from my tree diagram. And they drew it a lot prettier than me. What are you going to do? All right, what if you make this more complicated? It would be too many branches to deal with if there are more balls. So we simplify the process by having a branch represent multiple branches. So now in our urn, we have 11 balls. 3 are red and 8 are blue. Draw 2 balls again, one at one time with replacement. So again, we're going to have 2 draws. The tree diagram using these frequencies. Let's draw that. So again, here's my first draw. Now what I should draw are 8 branches that are all blue and 3 branches that are all red. That gets complicated way too fast. So what I do is I say, what could I do? I could draw any of my first balls to be blue. So the first draw, I have 8 chances of getting a blue ball. So you have 8 branches that are blue. And you have what? 3 branches that are red? So the probability of me drawing a red one, I have 11 balls, 3 of those are red, 3 out of 11. Okay? That's my first draw. What happens on the second draw? Well, if I drew a blue ball out the first time, I still have a chance with replacement of getting a blue ball 8 out of 11 times on the second draw. So my second branch, which again would be that 8 of them could be blue and 3 could be red. And over here, we could have 8 blue and 3 red. Okay, so what could happen here? Whoops. So the first branch represents that I could get 2 blues on the first draw and the second draw. And there are actually 64 outcomes, 8 times 8, where I could get the first ball as blue and the second ball is blue. So the number of outcomes in my tree diagram, total number of outcomes that are blue, blue would be 64. The second branch, where we have blue, then red, well, we could get 8 that are blue, and each one of those 8 branches, I could have 3 reds coming out of them. So I have 8 branches that are blue, and each branch has 3 reds. So I could have 24 that are blue-red. Now, if I look at the second branch in the first draw, oh, this is my second draw. We should label this second draw. If I look at the first branch in my first draw, my second branch in my first draw, I have 3 branches that are red. And from the first red branch, I have 8 branches that are blue. So I could again get 24 that are red, blue. Okay, and then the second branch in the second draw from the second branch in the first draw, I have 3 red branches, and each of those 3 have 3 red branches. So I have what, 9 that could be red, red. So this is my sample space. All my possible outcomes. So I could have 64 different outcomes where the first ball was blue and the second ball was blue. I can have 24 outcomes where the first ball is blue and the second ball is red. I can have 24 outcomes where the first ball is red and the second ball is blue, and then I have 9 outcomes in this sample space where both balls are red. So again, if you imagine this, in the first draw, I have 8 branches that are blue. And for each one of those 8 branches, I have 8 branches that are blue and 3 branches that are red. So that's where we get the 8B and the 8B and the 3R. So in the second draw, I have 3 branches that are red. And each of those 3 branches, I could have 8 blues and 3 reds. Okay, so there is my sample space. And how many items are in my sample space? You can add these up. That's one way of figuring it out. So there are 111 outcomes in my sample space. You could also look at this for a particular branch. You have 11 outcomes here, 11, 8 plus 3, 11 outcomes here. 11 times 11 is 121. You have 11 here, 11 here, 11 times 11 is 121. And theirs is much neater than mine. All right, So let's take a look at this tree diagram. Let me get the Zoom stuff out of the way. The first set of branches represent the first draw. The second branches represent the second draw. Each of the outcomes is distinct. In fact, we can list each red ball as R1, R2, and R3, and each blue ball as B1, B2, B3, B4, B5, B6, B7, and B8. Then we have three reds, R1 through R3, actually three branches represented by 3R. We have 8 branches that are blue, B1 through B8, so 8 branches. So just looking at the 9 RR, so the 9 outcomes in our sample space that are both red, that would mean that the first draw is red, the second draw is red. Or the first draw is red, and then from the second draw, you draw the second red. So there are 3 red balls in this bin, this urn. The first one could be your first red ball, and then the third draw could be on the second draw, you could draw the third red ball. So you could actually number these 3 red balls. So the 3 different outcomes you could get is that you draw the first red ball and you draw on the second one the same ball again. Okay, or you could draw the first draw, the ball that you labeled R1, the second ball is the ball labeled R2. So that's the second red ball. Or the last possibility on that first draw is you could draw the first red ball and you could draw the third red ball on the second draw. So the 9 different outcomes are represented here. R1, 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 R2, R1, R3. And then you have 3 red balls in this urn. So you could, on the first draw out that second red ball. And then on the second draw out the first red ball. So you could have R2, R1. Or on the first draw, you could draw out that second red ball. And then on the second draw, the second red ball again, because you're replacing it. Or you could draw out the third red ball and the second red ball and the third red ball. So you could do that. Or on the first draw, you could pull out that third red ball and then the first red ball. Or the third red ball and the second red ball. Or the third red ball and then the third red ball again, because you're replacing this each time. So you get 9 outcomes that are red, red, because you have 3 different balls that you're drawing out 2 different times. So 3 different outcomes on the first draw, 3 different outcomes on the second draw. 3 times 3 is 9. Okay. I think we've talked about that. Okay. List all the 24 BR outcomes. So list all the 24 BR. Right there. So what could you do? There are 8 blue balls. So you could do B1, R1, B1, R2, B1, R3. So the same blue ball on the first draw, and there are 3 different red balls on the second one. Or you could do B2, R1, B2, R2, B2, R3. Or you got a third red ball. So you could do B3, red 1, B3, red 2, B3, and I ran out of room. You see how this is going? B4, B5, B6, B7, and B8. Is that 24? One, two, three, four, five, six. 6 here, 6 here, 6 here, 6 here. Is that 24? Okay, I'm going to erase what I wrote. Using the tree diagram, calculate the probability that you get a red ball on the first draw and a red ball on the second draw. So R and R. How would you calculate that? How many different outcomes do you get in your sample space that are red, red? So what's your sample space again? Is it this down here? Is that your sample space?
Yeah.
How many outcomes in that sample space are red, red?
9.
9 out of how many total possible outcomes?
111.
111. 111, 121. 11 times 11 is 121. So the probability that the first one is red and the second one is red, there are 9 possible outcomes that are red, red out of 121 possible outcomes. The other way that you could look at this is that on the first draw, there are 3 out of 11 that are red, red. And on the second draw, there are 3 out of 11. So now the first draw is red. The second draw, there are again 3 out of 11 that are red. And these are independent possibilities. They're independent because you're replacing the ball. So the second draw does not depend on what the first draw was because you put the ball back in the urn. So the probability of independent events can be calculated by multiplying the 2 probabilities together. So the probability of red and red is 3 over 11 times 3 over 11, which is 9 over 121. So that's another way of approaching the problem. Independent events follow the multiplication rule. You can multiply the 2 probabilities together. The probability that I draw a red ball on the first draw, there are 3 red balls out of the urn with 11 balls in it. Okay, I've drawn out the red ball. I put it back in. What's the probability of me getting a red ball on the second draw? Again, it's 3 out of 11. There are 11 balls in the urn, 3 of which are red. So 3 over 11 times 3 over 11 is 9 over 121. Using the tree diagrams, calculate the probability that you get red, blue, or blue, red. Now this is an OR type probability. And these are mutually exclusive. You're not going to get red, blue, and blue, red at the same time. So if you have mutually exclusive events, you can add the probabilities together. So what's the probability of me getting red, blue? Is that 24 out of 111? What's the probability of meeting blue red? Is that 24 out of 111? Is that 48 over 111? Or how many outcomes are either blue red or red blue? Are there 48 outcomes out of the total 111 outcomes that are either blue red or red blue? So you can look at it both ways. So again, why can I add those two probabilities together? Because they're mutually exclusive. That means they can't happen at the same time. You can't have an outcome that's red, blue, at the same time as an outcome blue, red. That's not going to happen. It's going to be one or the other. What did I say? 111? Why are you letting me tell you it's 111? Is that 121?
It is, I added it.
Yeah. There's 121 outcomes here. 121 outcomes. And I'm confusing. Get this out of the way for a minute. 121. 24 over 121. 48 over 121. All right. All right. Get that out of the way. There we go. Using the tree diagram, calculate the probability you get a red on the first draw and a blue on the second ball. So you get a red on the first and a blue on the second. So which outcomes do we have where we get red on the first and blue on the second? Is that right there? So there are 24 outcomes in the sample space that are red, blue. So our probability of getting a red on the first and a blue on the second is 24 over 121. Okay, let's do a conditional. Using the tree diagram, calculate the probability you get red on the second, given you got a blue on the first. This reduces your sample space because now you're only going to look at the branch of your tree diagram where you got blue on the first draw. So you're only going to look at this half of the tree diagram. You're only interested, remember, conditional probabilities always reduce your sample space. So the only part of this tree diagram that shows blue on the first draw is that first half of the tree diagram. So what is the probability I get red on the second draw, given that I got blue on the first? So the probability of me getting red, given I had blue already, well, there are 24 blue reds out of my sample space, but my sample space has been reduced to 88. There are only 88 outcomes, is that right? 88 outcomes in that first branch where the first draw is blue. So the probability of me getting red, given the first draw was a blue, is 24 out of 88. All right, last but not least, I think this is the last one. No, we got one more. Using the tree diagram, calculate the probability of blue on the first and blue on the second. How many possible outcomes in your sample space are blue, blue? How many possible outcomes in your sample space are blue, blue?
64,
64 out of how many possible outcomes in my sample space?
121.
121. You could also look at this the way they did. If the first outcome is blue, you get 8 out of the urn of 11 balls. You got a probability of 8 out of 11 of getting a blue ball. You put that ball back in there. What's the probability of you getting another blue ball out? Well, you still have 11 balls in the urn, 8 of which are blue. These are independent events because you're replacing the ball back in the urn. So the second draw is completely and totally independent of the first draw. You still have an 8 out of 11 chance of getting a blue ball. So that's 64 out of 121. Okay, using the tree diagram, calculate the probability of getting a blue ball on the second draw, given that you drew a red on the first. Okay, so now we're only looking at this half of the tree diagram because we're only interested in the first draw being a red. So what's the probability of you getting a blue ball on the second draw? So the probability that you get a blue, given the first draw was a red, well, what do we get? Is there 24 out of, what are the total possible outcomes? 33? So there are 33 outcomes here where the first draw was a red. Out of those 33, 24 would be blue on the second draw. And they do reduce this in this example. There's a common factor of 3. For the most part, in your homework, they don't care if you reduce a fraction or not. Which leads me to a whole philosophical discussion about reducing fractions. It's one of those things that most calculators will reduce arithmetic fractions for you. Even the TI-84 will reduce an arithmetic fraction. So it's one of those cases your calculator will do this for you if you want to reduce it. So my open math, you can reduce or not. It's kind of up to you. Just be sure you read the instructions for the particular problem you're doing. Okay, Venn diagrams. Venn diagrams just represent a picture of your events and then your sample space. So the rectangle represents the entire sample space. And then each circle represents our particular event. And what's an event? It's just something you're interested in looking at. So what's the Venn diagram for this set of events and the sample space? Suppose an experiment has the outcomes 1 through 12, where A is the outcomes 1 through 6, and B is the outcomes 6 through 9. A and B, then where would A and B be? A and B are the elements the two sets have in common. So the element these two sets have in common is 6. So A and B, the intersection of these two sets is 6. A or B, you just take the two sets and join them together to get the union, the or. So A or B start at 1 and go through 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so what would your Venn diagram look like? So when we draw these in general college, general quantitative reasoning, I tell them to always draw the intersection first. So put the elements that are in the intersection of A and B in the little wedge, that's the intersection. So what goes in the intersection? The 6. All right, so then what goes to the left of the 6 in the event A? Every element that's in A except 6. So what's in A except 6?
1 through 5.
2, 3, 4, and 5. Okay, so then you go to B. What elements are in B that are not 6? Would that be 7, 8, and 9? I guess we should put commas between them so we know we got numbers. And then you do have elements in your sample space that are not in A or B, because your sample space are the numbers 1 through 12. And your union only goes 1 through 9. So you've got 3 elements, 10, 11, and 12, that are in your sample space that are not in either event. So you put those somewhere down here. And that is the Venn diagram that represents these 2 events in this sample space. So the sample space consists of the numbers 1 through 12. A are the numbers 1 through 6, B are the numbers 6 through 9. So A and B have in common the number 6. That goes into the intersection wedge. All right, now looking at the circle A must contain the elements 1 through 6, 1, 2, 3, 4, 5, 6. B must consist of the elements 6 through 9, 6, 7, 8, 9. Anything that's in the sample space that's not in either of those events, we put down in the sample space. Okay, suppose an experiment has an outcome black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal chance of occurring. Event C contains the outcomes green, blue, and purple. Event P is red, yellow, blue. Then C and P would be blue. The elements, those two events have in common. And C or green, C or P would be all the 2 sets put together. Green, blue, purple, red, yellow, done. Okay, so draw a Venn diagram. Okay, so the event, I should probably make this a little bigger. Maybe, can I? And the size does, I shouldn't say that, that comes out wrong. So what goes in the intersection would be blue, correct? And what elements are in, oh, these are C and P. Better label them, right? C and P. So what goes in C, green and purple? So does C contain green, blue, and purple? How about P? We got green. What I got a boo-boo here. Green, blue, purple. Okay. So P is red, yellow, and blue. So we what have red and yellow. Does that look correct? And then what's my sample space? Black, which I don't have listed. So let's put that down. White, which I don't have listed. Red, I have listed. Orange, I do not have listed. So let's put orange down. Go OSU, orange, black, and white. Woohoo! Go Pokes. What else do we have? Yellow, I got. Green, I got. Blue, I got. Purple, I got. So I think that's it. So we're teaching our 10-month-old grandson to say go Pokes. My 4.5-year-old refuses. I'm not gonna say that. Her dad graduated from OSU. We're a very OSU family. My husband and I both graduated. Son graduated. Daughter had a full ride, chose to go someplace else. Creighton, yeah. She had a full ride to OSU. And son-in-law went to OSU. Very OSU fan. All right. Now we get into these, some books call these the birthday problems. So we're going to do cards and then we'll actually do birthdays. What is the probability of getting 5 different cards? So no 2 or 3 or 4 cards of the same value from a standard deck of cards. So they're interested in face values. So they're not interested. So a 5 of clubs is the same as a 5 of spades. So those are the same cards. So in a deck, a standard deck of playing cards, you have 4 aces, 4 2s, 4 3s, 4 5s, etc. 4 jacks, 4 queens, 4 kings. Okay? So let's look. This is the way my brain works. Okay, so you have a standard deck of playing cards. What's the probability on the first draw you get a unique card? So let's say the first draw is the 2 of hearts. That's a unique card. What's the probability of me getting a 2 of hearts? Well, let's put it another way. What's the probability of me drawing out a unique card, such as the 2 of hearts? How many unique cards are in this deck? What's the probability of me drawing out a unique card?
1 in 52.
No.
Or 1.
1.
Oh, yeah.
Because it's going to be the first card. It's going to be unique, right? You haven't drawn any other cards out. So the probability of me drawing out a unique card without drawing any other cards out of the deck is 1. Okay? So that first draw is 52 out of 52. Okay? So now I had the 2 of hearts. So I take all the 2s out. Take all the 2s out. Would you believe the 2 of hearts is my first card in the deck? What's the probability of that happening? All right, all the 2s are out. How many cards are in my deck?
48.
48. What's the probability now of drawing out a unique card such as, oops, not 48. Oh, sorry. Got my brain. See, this is how my brain works. I leave the 2s in here. Leave the 2s in. I'm not taking them out. So I still have 51 cards in here. But how many of these cards are not 2s? 48 of these cards are not 2s. So what's the probability of me drawing out a card that's not a 2? 48 out of 51. Okay. So the 3 of clubs. Where's the 3 of clubs? I don't know. Where's the 3 of clubs? Oh, that's easy to find. Okay, now how many cards are in my deck? Got 2 sitting here. How many cards are in my deck? 50. How many of those cards are not 2s or 3s? 44. Because 4 of them are 2s. 4 are, in this case, 3s. So how many are not 4s or 3s? Well, the 44 that are left. Okay? Now, take the 8 of diamonds. I drew that out of my deck. It's going to be the last card in the deck, almost. Okay, how many cards are in my deck? 49. How many of them are not 2s, 3s, or 8s? 40. There are 4 8s. So 12 out of the deck of 52 are either 4s, 2s, 3s, or 8s. Okay, so the probability of me drawing a 4th card that is unique from the first 3 is 40 out of 49. All right, so what are we taking out here? Nine of spades. Out. How many cards are in my deck? 48. How many of those cards in my deck are not 9s, 8s, 3s, or 2s?
36.
36. How do I find the probability that I get that and that and that and that and that? So the probability of an and is going to be, we're going to multiply these probabilities together. Okay, so what do you get? You know, the way I would probably do this is using parentheses. I mean, this one's 1, so I can just get rid of that. So I would take 48 times 44 times 40 times 36, close the parentheses, use my division symbol, and then put in parentheses the 51 times 50 times 49 times 48. That's probably high to do that calculation on my calculator. Because you can multiply fractions together by multiplying all the numerators, correct? Multiplying all the denominators and then doing the division. What do you get? Anybody do it? This is why you don't win at poker. What's the probability of getting 5 different cards on a draw, on draw 5 cards? Does anybody do it? What do you get? Anybody get it? What'd you get? Did you get 0.7? You got 0.507?
Yeah, I think we're trying to make you calculate the odds, having a completely unique, of having 2 unique orders of cards, and like that's so big. There's more ways to arrange a deck of cards than there are atoms on Earth.
Oh, 0.5. Why do I have 0.7 written in my notes? It's 0.5. Oh, it's 0.7. How did I get that? 48 over 51, right? 44 over 50, right? 40 over 49, right? 36 over 48. Oh, one of us has multiplied it wrong. I don't know how they got that. 48. Okay, I'm like stubborn. 48 times 44 times 40 times 36. Close parentheses. Divided by 51.
Same answer they did, but not the same.
How did you do it to get the same answer?
But I did not get the same decimal.
Oh. Well, me too. It's 0.5. All right, so again, this is why poker is a game of strategy and not a game of luck. Because what's the probability you get 5 different cards when you play draw poker? 50%. There's a 50% chance you get 5 different cards. Now, if they're all 2, 3, 4, 5, 6, you know, if you get a straight, that's good. So what's the probability of getting a straight? You can calculate that. So poker is more of a game of strategy than actual luck. Unlike a lot of games, when you gamble at a casino, if you do the one-arm bandits, that's pure luck. Okay, what's the probability of 10 people in a room? What is the probability of 10 people in a room, nobody shares a birthday? Very high. Well, pretty high. Okay, so what's the probability, if I just randomly select one of you, that you have a birthday on a particular day? 1. Okay, what about the next person? What's the probability that they don't have the same birthday he has? 364 out of 365.
There's some unfortunate soul in here who was born on February 29th.
Yes, we are not counting leap years. I got engaged on February the 29th. February 29th, 1984. That's when we got engaged. So we don't have to worry about that engagement anniversary thing. All right. So now the third person, what's the probability that they don't have a birthday the same as the first two people? How many days are left in the year? 363 out of 365. So let's do this 10 times. Let's go ahead and write this as 365 over 365. What's that? 363 over 365. 362 over 365. How many have I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, and eventually we'll do combinations and permutations, and you'll see where this comes from. 358 over 365. Have I got them all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so how's the easiest way to calculate this? Well, I'd probably get rid of the 1. And then we have what? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 9 365s in the denominator. So probably what I would do is 364 times 363 times 362 times etc. to 358. And then I would divide that by, there are 9 365s in the denominator. So I'd do 365 to the 9th power. What you get? Oh, well, that's all right. What did I do wrong? Oh, times. Yeah, I can fix that. Go back over there and change that times to a divide. Do, 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 do. Something wrong with my calculation. It should be, what is it? Do you get 0.883? I don't know what I did wrong on my calculation. I'll have to go back and look.
I think you have to multiply all the way to 356.
I didn't, did I? That's what I didn't do. So the probability that you randomly choose 10 people and they all have different birthdays is pretty high. Almost 90% probability they'll all have different birthdays. It helps if you're able to use your own calculator. All right. What time is it? Bayes' theorem. So from earlier in the chapter, we got Bayes' theorem, which gives us the probability of an intersection of two events and a probability of events A and B occurring based on a conditional probability. So the probability of A and B occurring is the probability of A times the probability that B occurs given that A has already occurred. So the probability of B given A, which we can also write the probability of B given A by multiplying both sides of this or dividing both sides of this by the probability of A. Then the conditional probability, the probability of B given A, is the probability of A and B occurring divided by the probability of A occurring. Also, we can write the probability of B given A in terms of the conditional probability A given B. So the probability of B given A is the probability of B times the probability of A given B divided by the probability of A. Now, the difficulty you're going to have in your homework is deciding which of the probabilities is an and that they give you and which is a conditional. So a probability based on another event already occurring. So as you read your problems in your homework, read them carefully so that you can determine what's the probability of this and this occurring, or the probability of this occurring given that this has already occurred. And we'll look at one of your homework problems here in a minute. Okay. A tree diagram can be drawn using either frequencies or probabilities. And earlier, we drew a tree diagram based on frequencies. We had an urn that contained 8 blue balls and 3 red balls. And we drew a tree diagram based on the frequencies. Now we're going to draw a tree diagram based on the probabilities. The probability of having a type of cancer in a population is 0.03. So the probability you don't get this type of cancer is what? It would be the complement of having the cancer. So what's the complement? Is that 1 minus that probability? So there is a 97% probability, 0.97, that you don't get this particular type of cancer. All right? I should probably write that down here. All right, what else do we say? A test for the disease is 99% accurate if the person has the disease. So if you have cancer, this test is accurate 99% of the time. So it's accurate given you have the cancer. So the probability of it being accurate, saying yes, when you actually have the cancer, is 0.99. So given you have the cancer, the probability of you testing positive for this type of cancer is 99%. So what's the probability that you don't test positive and you have this cancer? Is that 0.01? So 1% of the people test negative even though they have the cancer. Okay, what else do we know? And it's 99% accurate if the person does not have the disease. So if I don't have the disease, I don't have any cancer, the probability of me testing that I don't have the cancer is 0.98. So the probability of me actually getting a negative result, given that I don't actually have cancer, is very high. It's 98%, 0.98. So what's the probability that I test no and I have? What am I doing here? I test yes and I have no cancer. Would that be 0.02? Okay, so now let's draw a tree diagram. And we're going to draw a tree diagram using these probabilities. So what's the probability I have cancer? That's going to be one branch. What's the probability that I don't have cancer? That's going to be the other branch. And then we're going to look at the test results for each of these branches. So the probability that I have this type of cancer is 3%. The probability that I don't have this type of cancer is 0.97, 97%. Okay, and then let's look at each of the branches. So for the people that have cancer, they actually have cancer, the test is accurate 99% of the time. It's inaccurate 1% of the time. For those of us who don't have this type of cancer, no cancer, then the test that indicates that we don't have that cancer is accurate 98% of the time. It's inaccurate 2% of the time. So 2% of the time, it will tell me I have the cancer when I actually don't. 98% of the time, it will tell me I don't have the cancer when I really don't have the cancer. Okay, so let's move the Zoom bar here so we can see. Okay, so here's the stuff I was given. The probability of having this type of cancer is 3%. So then, looking at this, the probability that I have this cancer and I test yes, so I test yes given I have the cancer is 0.99. The probability that I test no when I actually have the cancer is 0.01. That's that branch there. The probability that I don't have this type of cancer is 0.97. The probability that I test yes, given I do not have that cancer, is 0.02. The probability that I test no, given that I don't have the cancer, is 0.98. Okay, so what do I want to know? What's the probability that I have this cancer given that I've tested positive for it? So what's the probability of me having this cancer given that I have a positive test result? Okay, so using Bayes' theorem, I lost my pointer down there on the floor somewhere. So using Bayes' theorem, the probability of C given yes is the probability of C times the probability of yes given C. Those two I know. I was given that in the problem. Divided by the probability of a yes. That I don't know. I can figure it out from the tree diagram, which I covered up again. That'll work. Okay, so I can actually figure out the probability of a yes using the tree diagram. So I have two outcomes over here in my sample space that are yes, and these are probabilities. So to determine the probability of a yes, I multiply the two probabilities together. So from the first branch, I don't have this cancer, and the yes, I multiply those two probabilities together, and that gives me the probability of that yes up there. Or this yes down here would be the 0.97 times the 0.02. So I have two outcomes in my sample space that are yes. So I'm going to add those two outcomes together. So I have yes or yes, yes here or yes here. So I'm going to add those two together. So the probability that I have cancer given that it's a yes result is 0.6. So this is a matter of determining what you're given and then using Bayes' theorem to figure out what you want. This is one of your homework problems. A survey reported that 77% of registered voters in California approved of allowing two people of the same gender to marry. So what do we want to let our variables be? Maybe A be the event that they agree with same gender marriage. Okay, so what else do we have? Among 18 to 39-year-old registered voters in California, 86%, so let's write this down, was 77%, which is 0.77. Among 18 to 39-year-old registered voters, 86 approved of gay marriage, which doesn't surprise me that in that age group, you would have a higher percentage. So what you're looking at now is the number of people who approve of this, given they're in this age group. So this would be the probability that they approve, given they're between 18 and 39. And that's what, 0.86? Okay, what else do we know? So the probability that a registered voter is between 18 and 39 is what? 40%? Now, here's the question. Out of the voters who approved of gay marriage, what is the percentage that are between the ages of 18 and 39? So what percentage are between 18 and 39 given that they approved? Out of the voters who approved of gay marriage, what is the percentage that are between 18 and 39? So what's the probability of them being between 18 and 39 given they approved of this measure? And you can figure that out from Bayes' theorem. Okay, any questions? All right, we'll see you Thursday.